All right, let's get started with lesson 4, rate law, part 2. In part 2 of this lesson, we're going to learn how the order of the reaction affects the overall rate of the reaction when we change the concentrations of the reactants. We are also going to learn how to derive the units for the rate constant K. To begin with, we're going to look at a zero order reaction. Remember from part 1 that a zero order reaction, the rate law expression is simply the rate of the reaction is equal to the rate constant times the concentration of the reactant raised to the zero power, or the zero order. All right, well, any concentration raised to the zero power is just going to be simply 1. So therefore, the rate expression can be written as the rate is equal to the rate constant. And so in a zero order reaction, we're going to simply drop the reactant concentration of the zero order and just write rate is equal to K. Therefore, what that means is that the concentration of the reactants does not have any effect on the rate whatsoever. And so therefore the rate is just dependent on what the rate constant will be. All right? So therefore, as we mentioned, the reactants of a zero order are therefore not included in the rate law, which you can see by here. So the rate law for zero order is just the rate is equal to the rate constant. So therefore, what are the units for K? Well, if the rate constant is equal to the rate, then the units of K just are the units of rate. So what are the units of rate? Well, let's write those down. The units for rate are moles per liter per second. Now remember, 1 to the minus, or s to the minus 1 is just equal to 1 per second. All right, and the same thing with liters here is we're looking at moles per liter, and we're just taking the reciprocal of that. And that's typically how we're going to express the units of concentration here. All right, so therefore, if those are the units for rate, then the units for K for a zero order reaction must also be moles per liter per second for a zero order reaction. Okay? Now, if you're an IB student, then you're going to use a little bit different units for concentration. Those units are going to be expressed as moles per cubic decimeter per second. So therefore, the units of K for a zero order reaction will also be moles per cubic decimeter per second. All right, again, these are for IB students. All right, let's go to a first order reaction now. Remember that in a first order reaction, the rate expression would just simply be the rate is equal to the rate constant times the concentration of the reactant to the first power, which is the first order of the reaction. So therefore, the rate expression can be written as rate equals Ka. So what does this mean? Well, it simply means that when the concentration of the reactant is doubled, it should therefore double the rate. So in a first order reaction, the rate depends on the single reactant raised to the first power. All right, let's go to a chalkboard and let's actually do some examples here. Write out some problems. So again, the rate law is equal to Ka to the first order, okay? So let's say that A has a concentration of 1 molar, all right? So if we plug that into our rate expression, raised to the first power, then that means the rate is just simply K times 1. But if we double the concentration of A to 2 molar, then the rate is equal to K 2 to the first power, which is simply then the rate is equal to K times 2. So in other words, by doubling the concentration, we're going to double the rate. Okay, what if we tripled the rate, or triple the concentration? So let's say that A is 3 molar now. Well, in a 3 molar, we would say rate is equal to K 3 to the first power. So therefore, the rate would be affected by K times 3, which is going to triple the rate. So if I triple the concentration, I should triple triple the rate of the reaction, okay? So kind of see how a first order affects the rate when we change the concentration, double or triple or so forth, okay? Well, what about the units of K? All right, the units of K, since we know that the rate is going to be affected by the concentration, then K is simply found, K is found by taking the rate divided by the concentration of A to the first power. So therefore, the units of K are going to be dependent upon the rate, the units of rate, plus the units of the concentration. So again, the rate units are moles per liter per second, and the concentration units are moles per liter. All right, so let's throw these units into our expression here. So K, therefore, should have units of rate, which is moles per liter per second, over moles per liter. Do a little bit of algebra, and those expressions should be able to cancel out, leaving you with per second. So the units of K are just simply per second. All right, so for a first order, anytime you have a first order reaction, the units of K are always going to be per second. All right. Okay, let's go to a second order reaction now. So second order rate expression can be written as the rate is equal to K times the concentration of A raised to the second power, which is the second order. All right, and so the rate expression is written like so. So what does this exactly mean? How does the change in concentration in a second order reaction affect the rate of the reaction? Well, if the concentration of the reactant doubles, the rate should quadruple. All right, the rate of the reaction depends on a single reactant raised to the second power, or two reactants, each one raised to the first power. All right, so let's kind of look at this. Let's go to our whiteboard and practice how a second order would affect the rate. So I'm going to write rate is equal to Ka to the second order. All right, so if the concentration of A is equal to 1, and we throw that into our rate expression, 1 to the second. Therefore, the rate should be K times 1. But what if I double the concentration to a 2 molar? All right, we plug that into our rate expression, K times 2 squared. Therefore, the rate must be 4 times K. So therefore, if I double the rate, double the concentration, I should quadruple essentially the rate of the reaction. It should go up by 4 times. All right, what if we tripled concentration? Okay, throw that into our rate expression. So K, and how would that affect it? Well, the rate would simply be 9 times the value of K. So our rate of the reaction should go up 9 times as fast when we triple the concentration. All right. So you can see that the order of the reaction has a significant impact when we change the concentration of the reactants. It will impact the rate of the reaction quite a bit. All right. So how do we solve the units for a second order reaction? All right. Well, again, K is found by taking the rate over the concentration of A squared. All right. So if we write out the units of rate, that would be moles per liter per second over the concentration, moles. Oops. Let me rewrite this. All right. Let's rewrite this. So moles per liter per second over moles per liter. Those are the units of concentration, and we're squaring it, so then we really are multiplying by moles per liter again. All right. So using some algebra, you can cancel out that unit and that bottom unit there, and that should give us per second over moles per liter. All right. So if we take the reciprocal of the bottom unit so that we can get it up on top, we would simply write the units of K as moles minus 1 times liters times, or per second, times per second. All right, so these would be the actual units of K for a second order reaction. All right, so that would be mainly for IB or AP, but what about IB? All right, let's derive the units for IB really quick so that they can see this. All right. So remember that in IB you're going to have rate units of moles per cubic decimeter per second over concentration, which will be moles per cubic decimeter, and we're going to multiply that by moles per cubic decimeter because we're squaring the units there. Therefore, we can get rid of these top units. So if we do the reciprocal of those units, we would simply find that it would be moles minus 1 cubic decimeters per second. And so that would give us the units of K for again for a second order reaction. All right, so it's really important that you understand how the order of the reaction affects the overall rate of the reaction when we change the concentrations of the reactants. And is even more important, well, not even more important, but it is really important also that you can derive the correct units for K. And of course, it all depends, the units of K will all depend on what the order of the reaction is. All right, so let's look at a couple of other, let's look at some more examples here. So let's say you have a reaction where you have two reactants now. So the rate is equal to A times B. And let's say they're both raised to the first power. So A is to the first order and B is to the first order. Now in part 3, we're going to learn how we actually determine the order of each individual reactant. But for right now, I'm going to give it to you. So what we're going to say is that the overall order for this reaction is second order. Because remember, you're going to take the individual orders and you're going to add them together. All right? So since each one of them is 1, we're going to take 1 plus 1. That gives us 2. So the overall order for this reaction is second order. All right? So we can then derive the units just like we would normally do for a second order reaction. We would take the rate over A to the first, B to the first equals K. So the units of rate are going to be, again, moles per liter per second over moles per liter. That's for A. And then for B, it's going to be just moles per liter. That's for B. Those cancel out. Do the reciprocal of the bottom, and therefore we get moles minus 1 liters per second. Okay, again, no matter what, we get the same units for K for a second order reaction, even though we have multiple reactants. Okay, kind of see how that works. What if we had an actual third order reaction? So what if we had something like this? Again, we have two reactants. So the rate equation would be K. A, let's say A is to the first order, but now B is to the second order. So the overall order would be 3, because 1 plus 2 is 3. So the overall order would be 3. So how do we get the units for our third order reaction? Okay, so let's look at that. Again, K is equal to the rate over A to the first order, B to the second order. Therefore, the units of rate is moles per liter per second over the units for A, which would be moles per liter, and B would be moles per liter squared. Okay? So, how would we work this out? Well, we get rid of those units. We do the reciprocal of the bottom unit, and we should get units of moles minus 2 now, liters squared, and per second. All right? And that would be the units of K for a third order reaction. Really strange units, I understand that. But nevertheless, those are the correct units for our third order reaction. So again, we derived those. All right? So hopefully this helps. This is it for right now. Study these ideas really well and prepare for the quiz. And that's it for part 2 of Lesson 4 on the rate law.